As you can see, I rewrote all the useful information that we needed to solve part A of this problem right in front of us. Now the problem gave us two limits, 0 and 8. These limits represent the bounds of time. So I'm going to write those down in our integral. Next, we were also given a function, the flow rate into a pipe, which was measured by r of t. Now, College Board and Mr. Farrar both allow you to just write r of t if you define it. Since College Board already defined it for us, we can use their own shenanigans and just write it in there. Now, the reason why we're using an integral is because the total amount of water that flows into the pipe is equal to the area under the curve of the function r of t during those bounds. Now, when you solve for the function on your calculator, you should get 76.570 or something very close to it depending on how you round. Now I'm going to show you how to do this on a TI-89 calculator. Unfortunately, I don't have any other models of calculators, but if you know how to use bounded integrals on either the 84, 83, or whatever you have, you should be fine. Let's get started. So on the TI-89, how you're going to solve this problem is by hitting F3, then 2. That'll allow you to integrate. Now you're going to type in the function 20 sine of t squared divided by 35. And make sure that you integrate for t and that you give it the bounds of 0 and 8. Close the parentheses and you get the answer. Let's go on to part B. In this problem, College Board gave us two functions. The rate in, defined by r, and the rate out, defined by d. We can take the difference of these functions to figure out how much water is inside the pipe at any given time. College Board would like us to find the rate at a specific time, t equals 3. So we're going to solve for both of these functions at that time. Now we get that r of 3 equals about 5.086, and that d of 3 is equal to 5.4. Because the rate out is greater than the rate in, the volume of water inside the pipe must be decreasing at time t equals 3. So now I'm going to show you how to solve part B on your TI-89 calculator. In order to save time, I've input both functions into the y equals. If you do not know how to do that, please revert back to one of my earlier videos. Links will be in the description. So I'm going to access these functions using varlink. I saved y1 as my rate in. And I'm going to subtract, or take the difference, from y2, which is my rate out. Notice how I use 3 for both. y1 of 3 minus y2 of 3. Hit enter. Now, because the difference between them is negative, there is more water going out of the pipe than coming into the pipe. This means that the total volume of water inside the pipe is decreasing at t equals 3. Let's move on to part C. In order to solve part C, I've decided to come up with a function called L' of t. L' of t equals the rate in minus the rate out. This is how I solved the previous problem. Now, what I know is that a maximum or minimum has to have a derivative whose slope is equal to 0. Now, because L' of t is technically a derivative of L of t, I can set it equal to 0. And it will be equal to 0 at time of t equals t. I just chose the variable letter big T. That might make it kind of confusing later on, so I apologize. But this is how College Board would actually solve the problem. Is that they'll define a variable, they'll solve it, and they'll use it later. So what happens at this point is that time of big T will be approximately equal to 3.272. Now to finish part C, you have to get L of t. Now L of t, you have to use a piece of starting information that College Board gave you in order to actually find out. So if you notice this 30 here, that's from the starting piece of information that at time 0, the amount of water in the pipe is 30 cubic feet. Now I'm going to fill in my bounds on my integral from 0 to time big T. Now once you solve for this, you're going to get that it is equal to 27.965. And you're going to want to also check your endpoints. So A of 0 is 30, and A of 8 is 48.544. This means that your minimum will occur at time t equals big T, which is 3.272 hours. Let me show you how to do this on the TI-89. Because 30 is a constant and not inside of the integral, we need to make sure that we add it to the integral and not multiply it to the integral. Next, we're going to be taking the integral of L prime of t, which I did not input onto my TI-89. So I'm going to have to use my y1 of t minus my y2 of t. You could simply input this as a separate function, however I chose not to. Next, what you're going to need to make sure that you do is that you give it the variable in which to integrate for, t, and give it the balance. Now on this calculator, I can't store uppercase and lowercase variables without getting the two confused. So I chose to keep big T as A. It would be the same thing if you stored it as any other value. And as you can see, I get the 27.9646. So here I have an integral written. Now I've decided to use the upper bound of W. You can use whatever letter you want, as long as it's not some value you've previously used. Now you'll notice that the lower limit is 8. That's because it's set for t greater than 8. And you'll also notice I have an unknown, x. Now, x is going to be equal to something that we haven't yet solved for, unless you made sure to check both the upper and lower bounds for the last problem to see where maxima or minima would occur. Now, x is equal to L of 8. Which, if you remember correctly, equals 48.544. So, as long as you make it clear that x is this value, you can legitimately write x right here. And that is how to solve part D. Now, because it only asked you to write down a function and not actually solve the function, there's no calculator work, and you can move on to question number 2. Well, everyone, that's how to solve part 1. Thanks for watching, and if you have any problems with integrals, book chapter number 5 is just regular plain old integrals, and chapter 6 and 7 are different applications of integrals. So chapter 7 is closer to what we did here to solve for rates of time, along with chapter 5, and chapter 6 is how to use it to solve for areas and volumes and shenanigans like that. Well, once again, I hope this helped, and thanks for watching.